Greetings! This is the sixth lecture of EEE, and in this lecture, I'll be introducing to you the concept of alternating current and how to do circuit analysis in that domain. So these will be the topics we'll be covering: some fundamentals of alternating current or AC, what we call reactive circuit elements, and how to do a time domain analysis on those elements. So by far, we have discussed these topics right here, these four, and some DC machines. So that covers our past 5 lectures: basic circuit elements, electrical quantities, your nodes, loops, how to do circuit analysis using Kirchhoff's laws, and modifying Kirchhoff's laws to easily or to analyze circuits better by nodal and mesh analysis, some circuit equivalence, and the concept of DC machines. But in these and what we have discussed for the past 5 lectures, the voltages and currents are constant, or what we call direct current or DC. So let's differentiate that from alternating current. Direct current only flows in one direction. So just in this circuit right here, your current just flows in one direction, just flows in one loop direction. Alternating current, as you can see, cycles with time. So at one point, the current could flow this way, and another point, the current could flow the opposite way. So this is the concept of your alternating current. And it's mostly a sinusoid, right? So it flows in a sinusoidal manner, right? So it cycles back and forth between two maximum peaks, okay? So can we perform AC analysis as repeated DC analysis for each time instant? Um, let's say you're gonna consider time t1, then maybe current is flowing this way. Time t2, well, the current is now negative, so it's flowing in the opposite direction, or you can have your voltage source flipped like this here. But however, we cannot do that because there are circuit components, or there exist some components or elements whose characteristics are defined by a change in voltage or a change in current. And because we're only dealing with DC for the past 5 lectures, there's no change in voltage or current. Therefore, these elements do not react to that. And I'll introduce these two elements now. It's your inductor. The inductor is an element that basically reacts to a change in current. If there's a change in current, there's a change in voltage induced because of the inductance of the inductor. So this came from Faraday's law. Okay? So because of inductors, we can store electrical energy in the magnetic field and use it in other ways. So, but for now, we just know that it reacts to a change in current. So, we represent the inductance as L, and it's measured in henries, the SI unit for inductance. The relationship between the inductance and the voltage and the current is defined by this equation right here. So the voltage across the inductor is defined by the change in what we call flux linkage, d lambda over dt, which is equal to your inductance multiplied by your current. And since the inductance is constant, we have this expression right here, where the voltage across the inductance reacts to a change in current with respect to time. So we can solve for the current through an inductor by just solving this differential equation. Get this expression right here. So the current across an inductor is equal to an initial condition plus the integral of the voltage. Okay. Another element that reacts with the change in values would be the capacitor. Capacitor in this case reacts to a change in voltage. So there's a change in voltage, the capacitor reacts with current. Okay, so it looks like this, and it has an ability to store electrical energy through its electric field. Okay, so for your inductor, magnetic field; for capacitor, electric field. And we represent the capacitance of a capacitor with the variable C, and the unit for capacitance is farad, which is the SI unit for your quantity. The fundamental characteristic of a capacitor is that we have your, so the current is equal to the change in charge over time, but the charge in a capacitor is equal to its capacitance times the voltage across the capacitor. So since the capacitance is constant, we just flip that out of your, factor that out from your differential operator. We get this expression right here. Okay, so current is the result of a change in voltage. Okay, if you want to get the voltage across the capacitor, well, you just integrate that differential equation, get this expression. The voltage across the capacitor is equal to some initial condition plus the integral of the current. Okay, so with that, there's kind of a dual relationship between your inductance and capacitance, where basically they react differently. For a capacitor, it reacts to a change in voltage, and for an inductor, it reacts to a change in current. So, some more comments. For a capacitor, voltage cannot change instantaneously. Why? If there's an instantaneous change, then you need an infinite amount of current. So an instantaneous change is basically big change, infinity. That means this will become infinity. For an inductor, current cannot change instantaneously. If it changes instantaneously, then this term will be infinity, then the voltage becomes infinity. Okay. So if you have a capacitor in your circuit and the voltage is constant, then the current is zero. And capacitor likes to act as an open circuit in DC. If the current is constant, this change will be zero, then the voltage is zero. Therefore, it will act as a short circuit, which makes sense. Let's go back. For inductors, it's just a wire that is coiled in this way. It's just a wire. If there's no change in current, then the current will just flow through the wire as if there is no element there. Okay. For a capacitor, it's an open circuit. Between these two conductive plates is what we call a dielectric, which is an insulator. So there's no current passing through this region right here since this is an insulator. Okay. So if there's no change in voltage, there's no change in current. Sorry, there's no current that is going through the capacitor because there's no induced displacement current, as we call it, from this plate to the other plate. But anyway, it's just an open circuit. There's no change in voltage. Okay, but once we are gonna analyze it in alternating current domain, AC domain, well, you have to consider these elements and how they change, how do they react with the change in quantities. So for inductors in series, okay, so let's look at the combinations. Of course, we can connect them in series and parallel also. For inductors in series, well, you just basically add them up. Okay, how did that happen? They have the same current. Okay, so they have the same current but different voltages. And you want to get the effective inductance with that, you can solve it using Kirchhoff's voltage law. We get this expression right here. For inductors in parallel, well, just think of them as resistors. So that's 1 over the reciprocal of the equivalent inductance is equal to the sum of the reciprocals of the individual inductances in parallel. For a capacitor, it's a different story. Capacitors in series, you need to uh, quote unquote do a parallel operation to them. Okay, so they are in parallel if they are in series. So it's kind of weird if you think about it. But capacitors in series act like they are parallel circuits. Okay. For capacitors in parallel, the easy one, you just add them. right? So that's how your capacitor and your inductor kind of are dual of each other because they are the opposite of each other if you think about it. Okay, so now these are new elements that you have to add in your circuit analysis. So next, let's look at the sinusoidal function as described by this. So a sinusoid function in time has an amplitude, uh, frequency, and a phase. Okay, so the phase is the phase at t is equal to 0. So right here. So it's basically the phase shift of your sinusoid. Okay. Some definition: the frequency of the sinusoid is basically how many cycles the how many cycles the sinusoid, no, what do you call this? Basically, how many times it rotates in 1 second. That's the frequency, which is 1 over the period of the sinusoid, period t, which is the time it takes for the sinusoid to create one cycle. So if this is your sinusoid expressed in omega, which is your angular frequency, you can express the sinusoid in the actual frequency using this expression right here. There's a 2 pi multiplied to the frequency here. In the Philippines, the nominal voltage described by this expression right here. So the amplitude of the sinusoid on your outlets is 311 volts, and the angular frequency is 377 radians per second. Or if you convert it to frequency, you get 60 hertz. Okay. With sinusoids, we have the concept of leading and lagging. Consider then these two sinusoids here with different phase shifts, 60 degrees and 30 degrees. So F1 of t is the blue, and F2 of t is the red. Okay. So we say that F1, the one here, leads F2 by an angle of 60 degrees. Why? Because when F1 rises, your second sinusoid is not yet at that point. So it rises at a later uh, time, or it has a delay in its rising point. So that's why the first sinusoid leads the second sinusoid. Okay? Or we can say that the second sinusoid, F2 of t, lags F1 of t by an angle of 30 degrees. Okay? So let's look at the behavior of each circuit element when we have a sinusoidal voltage across those elements. First, the resistors. Consider, let the current across the resistor be this function right here. By Ohm's law, we get the voltage. So just multiply the resistance R. You get this expression right here. So you can see the voltage function and the current function has no phase difference whatsoever. Therefore, we call this condition in phase. So the current is in phase with the voltage. For inductors, let the current be this expression. If we plug it into to get the voltage of the inductor, so we just get the derivative, we'll get this expression right here. Okay, so if you're gonna plot that, your current is a cosine function, so it's this one. Your voltage is a negative of a sine function, which is this one. Right? So with this, we can see that the current lags the voltage by 90 degrees. The voltage leads the current. So if we extend this drawing here, the voltage rises first before the current rises. Therefore, the current lags the voltage. And in this case, it's 90 degrees. So how do you get that? You just need to express this sine omega of t as a function of cosine. So it's just basically, sine is just a phase shifted version of cosine. Therefore, this expression, we include the negative. We want it to be positive here uh, in this expression here. So you get cosine So this is your voltage cosine omega t plus 90 degrees. Okay, so this is the uh, sinusoidal function of your voltage, which actually leads the current by 90 degrees. Now let's look at the capacitor. If we let a current uh, I sub m cosine omega of t flow and get the voltage across the capacitor, we get this expression right here, which is, if we express it in terms of cosine, it's cosine omega of t minus 90 degrees. Okay, so in this case, the current leads the voltage by 90 degrees. So the current rises first before the voltage rises. So there's a delay of 90 degrees from here to here. Okay, so that's the behavior of your capacitor, inductor, and resistor when subjected with a sinusoidal current or alternating current. So just some notes: in a resistor, again, your current and voltage are in phase. In an inductor, your current lags the voltage by 90 degrees, and in a capacitor, your current leads the voltage by 90 degrees. So it can be shown, just some notes, it can be shown that if we have a combination of in series of a, no, not necessarily in series, if we have a network that is purely resistive and inductive, the current lags the voltage by an angle in between 0 and 90 degrees. For example, if we have a resistor in series with an inductor, okay, if we measure the voltage here, so some voltage V0, and has a current going in that is I0 here, then this current lags the voltage by an angle between 0 and 90 degrees. For an RC network, the current leads the voltage by an angle of 90 degrees. So that means it's just a network consisting purely of resistors and capacitors. Now, if we have the combination of the three, either one or two will hold, so we don't really know what would happen. Okay, so you have to solve it. So I'll show you in succeeding lectures how to determine that. Alright, so now we know how the voltage and current behave in the three elements if it's an alternating current. Then we want to know, or what we're interested in is the power across each element. So we define then what we call an effective value of a sinusoid that represents the power that is flowing through the elements. So consider first a constant current I and some AC current that is I sub m cosine omega t. Okay. So we can say that the effective value of this alternating current is equal to the effect of the DC current I if their average power is equal in the same resistor. So that's what it means when you get the effective value of a sinusoid. So if the power equal to VI, which is, if you want to express it in terms of current and resistance, it's just I squared times R. So since the current is constant in the DC case, then the average power is just I squared times R. So for a alternating current, first we need to get the instantaneous power. So just multiply I by itself and multiply to R. Get this expression right here. If we want to get the average power, so first you convert this expression into this. Okay? So that's the half angle formula. And notice that if you distribute these terms, you'll get this expression right here. The average power for, the average of this expression is that this term will be 0 because this is a sinusoid. The average of a sinusoid is 0. This term is constant, so it won't be 0. It will still the same. It will stay the same. Excuse me. Then the average value for an AC or a sinusoidal function, the average value of the power is equal to this. So equating the average powers, so this is for DC, this is for AC, you can solve for I sub for the effective current across of the sinusoid across the resistor. Get this expression right here. Okay. So this is the effective value of a sinusoidal current with amplitude I sub m. Okay. So this is just for current, but the same definition applies to a sinusoidal voltage. We call this the root mean square value, RMS. So the root mean square value for in general actually for a periodic function, you'll get you use this expression right here. You take the sum of the square of the function. In this case, since it's continuous, you integrate the square of the function in one period and divide it by one period and take the square root. You get the root mean square. Nominal voltage in the Philippines is 311 volts for amplitude. The effective value of that is 220 volts. Okay, so let's have an example. So consider the network shown. So let Vm, let V of t be Vm cosine omega t, where Vm is your and omega is constant. So find the steady state current I. By doing KVL in this loop, so let's let the current direction be here in this direction. Then the voltages across each of the elements would look something like this. I forgot to note. If the flow of the current across the inductor and your capacitor defines the polarity of those elements, just like the resistor. Okay, so if you do KVL, you get this expression right here. This is the voltage across the inductor, the voltage across the resistor, and your source voltage. So to solve this differential equation, we let I be equal to this expression. Okay, so substitute that to this expression, get the derivative, get this expression right here. By substitution, okay, substitution, we get this. So since cosine and sine are orthogonal to each other, we can just compare coefficients to solve for the unknowns a and b. Okay, so comparing coefficients, we get this expression. We can solve for a and b. So to solve simultaneously, just solve for a and b, and a becomes a function of Vm, b becomes also a function of Vm. Right? So just substituting that to the original expression, the steady state current will become this. Right? Or if you want to express it in terms of cosine, it becomes this expression right here. Right? So another example. Find the differential equation that describes the mesh currents I1 and I2 in the network. So these are mesh currents. Okay? So we can apply the same mesh analysis to the functions, to the circuit, sorry. So for mesh 1, we have 8 ohms times I1 plus 1 over 1 over 16, which is 16 capacitance, integral of the current flowing through the capacitor, which is I1 minus I2 dt equal to the voltage. So that's KVL in this loop, and we expressed the voltages in terms of the mesh currents. Mesh 2, same analysis. Okay, first we go through here, 1 Henry times the derivative of the current flowing through here, plus 10 times the current, plus 1 over 1 over 16, or the reciprocal of this capacitance, and then integrate. Okay, so integrate, in this case, it's I2 minus I1. So again, recall your mesh analysis. Right? Solving simultaneously. So first, differentiate both to make the integral operators disappear. Get these expressions right here. Okay. So it's actually tedious to write the expressions of the derivative. Let's just let the derivative operator be equal to this. Okay, and you substitute that, you get this expression for equation 1. this expression for equation 2. Okay? So next, we just need to solve it simultaneously. Okay? So we have to cancel the current expression for I2. If we want to cancel I2, sorry, we want to cancel I1, sorry, not I2. Just multiply the first with 16 and we multiply the second with 8b plus 16. And finally, adding those terms, I1 will cancel each other. You add this, I2 will be left. You get this expression right here, which you can simplify into this expression. Right? So how did that happen? Divide the common factors. So you can factor out 8d in this expression inside. Right? Factor out 8d. And you divide it from this expression. And you'll get this. Okay? So the differential equation for the current I2 is this expression right here. Similarly, we can solve for I1, okay, and simplify that again, okay. So we get this expression for I1, right? Right? So if you have any questions, just leave a comment on the video. Okay? So just one last note. If you look at the coefficients for if you look at the coefficients for I2, different the expression for the differential equation for I2 and I1, they're actually similar. Okay? So here and here, right? And the only thing that differs is the left-hand side expressions. Okay? So we call this actually, since this is the same for each variable on the circuit right here, call this the characteristic equation of your circuit. Okay? So this same coefficients, same derivatives, etc., etc. We call this the characteristic equation. Right? So if you have any questions, again, leave a comment. Okay? Or we can discuss this in class. And I'll see you next time.